All right, good morning, everybody. This is Mr. Rhett, and we're going to learn about using Newton's laws to solve problems. This is arguably the most important section in all of grade 11 physics, so pay close attention. And we're basically going to be doing this for several weeks using different types of forces, solving different types of problems, using Newton's laws in different ways. So this is really fundamental thing to get started with. With the power of Newton's laws, we can figure out how satellites orbit, how to design safer cars, and how blocks slide down ramps, and other such very physicsy problems. Look, Newton's laws of motion are not that complicated, but they are extremely powerful if you understand them and how to use them. So let's just review what they are first of all. The first law is that if the net external force on an object is zero, the object will remain at rest or continue to move at a constant velocity. You have to really deeply understand what net force means in order to understand this law. That is basically the sum of all the forces acting on the object when you kind of add them all up, balance them all out. The second law is simply the equation force equals mass times acceleration. If there is a net force acting on an object, it will accelerate the object depending on the mass of the object and the size of the force. And third, which you just learned about this week, for every action force, there is a simultaneous reaction force that is equal in magnitude but opposite in direction. Okay, look, these forces are really not that complicated, and yet they governed the physics of moving bodies for hundreds of years, and still to this day, mostly they work, except when we look at really, really large and really, really small objects moving at extremely high speeds. But for everyday objects, that you observe in everyday life, these laws basically work. They're not that hard to understand, but they are hard to apply. So that's what we're going to start to do today. Oops, I didn't mean to, let me just change this up a bit. Okay, so let's just review the types of forces that we've seen so far. We have the force of gravity, which basically always acts on as long as we're on Earth or some other planet, always acts downward. The normal force is the force of surfaces. So for example, it always acts perpendicular to the surface. So for example, a table pushes up on a book or a wall pushes back against a person leaning against it. It doesn't have to always act upward. It just has to act outward from the surface itself. The force of tension is basically the force of ropes, strings, cables, etc. My first year civil engineering professor always said, "You can't push on a rope." It's a good little quote to remember. The force of friction always acts in the opposite direction to the motion of the object. Like if you're driving down a road, friction is pushing back on you, that sort of thing. And the applied force is just a catch-all term that we use for a force that someone applies. Like if you're pushing on an object or lifting an object, we call that the applied force. You don't need to make up a new name every time, like, pushing force, lifting force, pulling force, etc. We can just call it an applied force. Okay, so that's there isn't really like a theory here. There's just basically practice with different types of questions, and we're going to go through over the next several weeks. We're going to see lots of different types of questions with lots of different types of forces, but basically we're just going to be applying Newton's laws. So it really comes down to practice. So when we do these example questions, the most important thing is that you stop the video and try the question yourself before I solve it, because it's really by far the best way to learn something, to learn this specific topic and skill, is to try it yourself, not to watch somebody else do it. So please, I am urging you, pause the video at the beginning of every single example and try it yourself before you watch me do the solution. So this is the moment. This is the moment that you pause the video and try it yourself. Okay, so we have a mass hanging on a string from a ceiling or something like that. The object pictured has a force of gravity of 120 newtons down. Determine the force of tension in the string. So here's the free body diagram. The object here is in the center, represented by the black dot. we have two forces. The force of gravity is acting downward, and the tension force is acting upward. Now, this object is at rest. It is not moving, which means it is not accelerating, which means, according to Newton's second law, if there is no acceleration, then there is no net force, which means that the tension force must balance the gravitational force, and so it must be equal, but in the opposite direction. So it's 120 newtons up. Example number 2. We have the exact same object, the exact same force of gravity, but this time the tension, like the string, bends around a pulley and is attached to a wall horizontally instead of hanging from a ceiling. So determine the force of the tension in the string in this case. Pause the video and try it yourself. So once again, here's the free body diagram. Remember, the free body diagram is just the forces acting on the object. So just because the rope bends around the pulley over here, that direction doesn't really come into the free body diagram, because the rope acting on the mass at the point of contact is pulling upward, not pulling to the side. So the free body diagram is exactly identical to the one before. So the force of gravity is still 120 newtons downward, and the object is still at rest. So therefore, the force of tension is still 120 newtons upward. And this sentence that I've bolded here is a really key point to make. The tension is the same at every point in a string, even if it bends around a pulley. So the tension right here is 120 newtons in the string. The tension over here is also 120 newtons. You don't have a different amount of tension at different points in a string, even if they bend around pulleys. And as a demonstration of just this, think about pulling a string tight. If you have a string attached to a wall and you pull it tight, it's not like part of it is tight and part of it is loose. The whole thing is equally tight all the way through the string. So yeah, that's a little explanation of why the tension is always the same all the way through a string. Unless you have it pinched, or if you've actually sort of like split it into two sections of string. But a pulley doesn't do that, because a pulley is still maintaining the tension. Example number 3, we have the exact same object, except there are two of them, and they are attached by these two pulleys going around sort of, I guess, like a ledge which is fixed to a wall. And so you have to determine the force of tension in the string. Pause the video and try it yourself. So here is a free body diagram, and this is an FBD that is the same for both objects, because they are identical objects. So you have a force of gravity going down, which is exactly the same as the last two questions, 120 newtons down, and you have a force of tension going up. Well, once again, these objects are at rest, meaning they're not accelerating. So the net force must be 0, so the force of tension must exactly balance the force of gravity in order for the objects to remain at rest. And so therefore, it's 120 newtons. Once again, same answer for all three questions so far. Let me just point out, some people think the tension is twice as much in this case because there are two weights, but this is wrong. And you just need to look at the free body diagram to understand that. If the force of tension was twice as much because there were two weights, then there would be a net force upward. It would be greater than the force of gravity and would cause the block to accelerate upward. But if that was the case, it doesn't make sense for both blocks to accelerate upwards simultaneously. That just wouldn't happen. So that's wrong. Okay, let's move on. Let's move on from those blocks and rope questions. This one's a bit different. So we have 3 sleds all attached by ropes. So we have 2 ropes, rope A between sled 2 and sled 3, and rope B between sled 1 and sled 2. Somebody is pulling on the whole system of sleds over here on the right side with a force of 120 newtons to the east. And there is no friction because this is going across an icy surface. And the masses of each sled are given, 12 kilograms, 11 kilograms, and 7 kilograms. So there are 3 parts to this question. You have to determine the acceleration of the sleds, the magnitude of the tension in rope A over here, and the magnitude of the tension in rope B. Pause the video and try it yourself. Okay, starting with part A. Here's what we're going to do. So the acceleration of the sleds has to be the same for all three sleds because they're attached. Just think about pulling on the front. If you pull on the first sled and it starts to accelerate, well, the other sleds are going to accelerate at the same rate because they're attached. So they're just going to follow the motion of the first sled. So the easiest way to solve this is to combine all three sleds into a single free body diagram. You can basically treat them as one object for the purposes of figuring out the acceleration of the system. So here's the free body diagram. We're going to have the force of gravity downwards and the normal force upwards. Now, you don't actually need to calculate those numbers because they don't affect the answer at all. You know that they're equal to each other. Whatever the number is, doesn't really matter. Force of gravity equals force of normal, and they're balanced. The one that we actually really care about is the applied force, which is 120 newtons to the east. Okay, so then the total mass of all three sleds is 30 kilograms. And according to Newton's second law, we know that acceleration is equal to force divided by mass. So you can just plug in those numbers. 120 newtons divided by 30 kilograms equals 4 meters per second squared. And that's to the east. And I should have included the direction in my answer there. I'm not really using proper notation here because it's kind of annoying on the computer to put in all the vector symbols and stuff like that, but you should be including proper notation when you do your solutions by hand. Okay. Part B, calculate the magnitude of the tension in rope A. Okay, now in this case, I'm going to draw the free body diagram of sled number 3 because I could do sled number 2, but it's more complicated because it's got two ropes attached to it, rope B and rope A. Sled 3 is easier to deal with because it just has that one rope attached to it, so it's going to be easier to solve. So here's the free body diagram. You've got, once again, gravity and normal force, which are balancing each other out. Don't matter. You don't need to calculate them. You know they're balanced. And then we have a force of tension to the right. And I'm calling that FTA, so force of tension of rope A. And we don't know how much that is. Now, you might think that it's 120 newtons because the person pulling over here is applying that much force. And maybe it is, and we're going to solve the problem, and maybe it'll turn out to be the same force. But don't just assume that it's the same amount of force just because all these things are attached. You need to make sure that it actually follows Newton's laws. So we're going to apply Newton's laws to figure out what the force is. So here's what we know. We know that the acceleration of sled 3 is 4 meters per second squared from the previous question. We also know that the mass of sled 3 is 7 kilograms. So therefore, the net force must be mass times acceleration, which is 7 times 4, which is 28 newtons. So actually it turns out that the force acting on sled 3 is not the same as the force being applied by the person over here on the right side. It's actually much less. And that's the way that Newton's laws cause it to work out. And so that's the end of that question. And part C says, calculate the magnitude of the tension in rope B. Okay, so rope B is a little bit more complicated. Once again, we have two choices. We could draw the free body diagram for sled 1 or for sled 2 because both of those sleds are attached to rope B. I have chosen to do the FBD of sled number 2. Okay, so here's what it looks like. We've got the gravity force downward, the normal force upward. Once again, we don't need to calculate that. It doesn't matter. They balance each other out. We have the tension force of rope B pulling this sled to the right, and that's not all. This is the tricky part. We also have the tension force of rope A pulling sled number 2 to the left. Now this part is sort of confusing because in the last question we saw that this rope was pulling sled 3 to the right, but now I'm saying it's pulling sled 2 to the left. Okay. Ropes are kind of weird. Ropes pull in both directions, right? Think about a tug of war. One team is pulling the other team, and then, team A is pulling team B, and team B is pulling team A. So the rope is actually pulling in both directions, depending on what end of the rope you're on. The tension in the rope goes both ways. So as it applies to sled 2, rope A is acting towards the west. and rope B is acting towards the east. And so there's going to be a net force here. Obviously, FTB has to be greater than FTA because we know that the sled is accelerating towards the east. And so the net force must be in the east direction. And that's why I've drawn the vector symbol here longer than the vector symbol over here. Okay, so here's what we know. Once again, sled number 2 has the same acceleration as all the other sleds, which we solved in part A. It's 4 meters per second squared towards the east. We also know that the mass of sled 2 is 11 kilograms. That was given in the question. So therefore, the net force acting on sled 2 is mass times acceleration, which equals 44 newtons. But remember that, so that doesn't mean that FTB equals 44 newtons, because we also have the FTA acting in the other direction. So the net force is the difference between these forces. So basically FTB subtract FTA must equal 44 newtons. So we can basically plug those numbers into this equation here, F net equals FTB minus FTA, and solve for FTB, which equals 72 newtons. Now if you want to, and that's the last example, but I just want to make a last little point here. If you want to double check these numbers, we now know everything in the question. We know the acceleration of all the sleds, which is the same for all of them. We also know the tensions in each of these ropes, but we didn't actually solve sled 1. So if you want to double check the numbers, you can actually kind of go through it and check it with sled number 1 and see if it works out. So on sled 1, you have 120 newtons to the right and 72 newtons to the left. That means there's a net force of 48 newtons. And I believe the mass of sled 1 was 12 kilograms. So if you do net force, 48 newtons, divided by mass, 12 kilograms, you get 4 for the acceleration, which is what you expected to get because that's what you solved at the beginning. So that's like a good way of double checking that your answers are all right. Okay, so that is it for this lesson. Now, this is not the whole section in the textbook for 3.5 because we also need to get into applying Newton's laws to problems that have some kinematics in them. This stuff didn't really have kinematics in it. It's really just Newton's second law. But I thought that was enough for today. So please, after you've gone through this video and tried these examples, you just have 2 questions to try, because this is a fairly long video with a bunch of examples. So just try these 2 questions and that is going to be it. Okay, thanks for watching.